So in this lecture we will see how to design a constant K low pass filter. So in order to get constant K low pass filter, since it is a constant K filter, the condition is that Z1 and Z2 bar are of opposite reactances, and further for low pass filter Z1 should be inductor and Z2 should be capacitor. Let us consider them like that. Okay, so in that case Z1 bar will be j omega L, Z2 bar will be 1 by j omega C, which is nothing but minus j by omega C. Fine. Now what is nominal impedance for constant K filter? It is nothing but K, which is equal to square root of Z1 into Z2. So with that you will get square root of L by C as nominal impedance. Fine. Remember these terms, all these terms have to be derived for all the different types of filters. Okay, this is for low pass filter. Next, all the same parameters will only be considered for high pass, band pass as well as band stop filters. So all these have to be determined for all the filters. So what is the second one? Second one is cutoff frequency. So the cutoff frequencies are going to be obtained when Z1 bar by 4 Z2 bar is equal to 0 and Z1 by 4 Z2 bar is equal to -1. Why this is, or why these are the conditions? So if you see the or go back to the characteristics of filters, so these are the values at which the cutoff frequencies are occurring. That means the end of stop band or starting of the pass band or whatever it is, at that these values are there. So you just go back to the characteristic of filters. So there are significances of pass band as well as stop band where these values we got. So accordingly, when Z1 bar by 4 Z2 bar is equal to 0, it means Z1 is 0, that means omega is 0 and F is 0. Fine. Similarly, when Z1 by 4 Z2 is -1, then it means Z1 is equal to -4 Z2. So when you substitute Z1 and Z2 values here, you will get the condition of omega C, that is 2 by root LC, whereas FC, which is in Hz, is 1 by pi root LC, because omega is nothing but 2 pi f. So if you substitute that, you will get frequency, cutoff frequency in Hz, right? So this is how we are going to determine the cutoff frequency for low pass filter, because these two conditions are important. That's why I told characteristics of filters are the basis for deriving or designing the filter concepts. Fine. So that means here the pass band starts at f is equal to 0 and continues up to the cutoff frequency fc. So all the frequencies above fc are in attenuation or stop band, right? They are corresponding to the values of 0 as well as -1. Okay, fine. Now let us see what is the value of attenuation constant. So we all know attenuation constant or attenuation is 0 in pass band, because there should not be any attenuation for the input supplied signal. But in stop band, the alpha is equal to 2 cos h inverse square root of modulus of Z1 by 4 Z2. So these two also we got them in the concept of characteristics of filters. Again we are going to use them. So what is this Z1 by 4 Z2 for this low pass filter? We already got it. Okay, so if you substitute them, we will get Z1 by 4 Z2, which is omega square LC by 4, because Z1 is omega L and Z2 is 1 by omega C and 4 is there as it is. Okay, so with this you will get 2 cos h inverse under root omega square by omega C square by substituting omega C, which is 2 by root LC, and other remaining term is considered as omega, sorry, it is already there as omega square. Fine. Now since omega is dividing with omega C, 2 pi will be cancelled. If you write it as frequency in Hz, then you will get 2 cos h inverse of f by fc. Fine, right? Now the attenuation constant alpha is 0 throughout the pass band, but it is increasing gradually from the cutoff frequency in the stop band. Okay, so this variation of alpha is given in the figure 15.5. okay, if you observe, till cutoff frequency there is no attenuation, it is pass band because it is low pass filter. That's why lower frequencies below FC are being passed, that's why alpha is 0, and after FC gradually attenuation is increasing. Okay, that means the input signal is passed through the system through some attenuation and it is gradually increasing. So why this is happening? This is due to this expression. Okay, it is very clear. Fine. Okay, now let us see what is phase constant. So this phase constant and attenuation constant are part of propagation constant. So we have got alpha values in pass band and stop band. Now let us see what are the values of beta in pass band as well as stop band. So these beta values are also derived through characteristics of filters, and that is equal to 2 sine inverse of square root of z1 by 4 z2, and if you substitute values of f and fc you will get this. And similarly in stop band beta is equal to pi. Okay, it can also be minus pi, but we are not going to consider minus pi in this case because the beta is gradually increasing with respect to f. So when it is increasing from 0, it has to go to positive pi angle only. That is its meaning. Okay, we will also get minus pi value in some particular cases, that I will tell you that time why it is minus pi. Okay, right. Now what is the characteristic impedance for this low pass filter? So we all know Z0 T, T indicates T type. If it is the T type filter of low pass, then what will be the characteristic impedance? So this Z0 not indicates characteristic impedance and the formula is this one. We all know this. Okay. Now if you substitute those values of Z1 and Z2, we will get this as Z0 pi, this is for pi filter, and Z0 T is this one. See, both are different. So the shape of filter also determines or decides characteristic impedance. Right. Now if you plot the characteristic impedance versus frequency, you will get this plot. So remember Z0 T is for T type or T shaped filter and pi is of pi shaped filter. Okay, and it is equal to K at 0 values of value of frequency f. Okay, so from that you can say the characteristic impedance Z0 T is real when f is less than fc, and at f is equal to fc it is 0, and for f greater than fc it is imaginary in the stop band and rising to infinite reactance at infinite frequency. Similar things can also be obtained for pi type low pass filter. Okay, right. Now we will see how to design the filter. So the design equations are these. We have k equals to square root of L by C and Fc is equal to 1 by pi root LC. So if you solve these two equations, you will get L and C values and you keep them here in place of Z1 and Z2. That is, anyways, it is Z1 by 2 in case of T, and here it is 2Z2 in case of pi. So like this we are going to design the low pass filter. Right, that's it. Thank you.